Okay, in this video I'm going to give you a basic introduction to the idea of a chemical equilibrium. A chemical equilibrium is when we have a closed system, so the particles can't leave the system, and both the forward and reverse reactions are possible. So imagine the reaction A plus B going to form the compound AB, and its reverse reaction AB going to form A plus B again. So we could start our system with A and B and A and B and A and B. And then maybe sometime later these guys might react up a bit and you'll have some A's and some B's and maybe an A and a B still floating around. And then with that all, so that happens over time. But what can also happen is that these ABs can split back up into A's and B's individually. And so both the forward reaction, where maybe an A and a B come together to form AB, is possible, and the reverse reaction, where an AB splits back up into a separate A and a separate B, is also possible. So these two reactions are going to compete with each other. Partners are going to get together, and they're going to split back up. And what's going to happen is, since both of the rates of these reactions depend on how many individual A's or B's or compound ABs exist, eventually they'll react back and forth until they reach a point where there's a stable number of ABs on their own and AB compounds. So maybe some ratio will exist between these two things in this system. And what ends up happening is the rate at which these guys might partner up to form ABs becomes equal to the rate at which ABs split up and form A and B separately. And so the population of A, or the concentration of A, and the concentration of B, and the concentration of AB all become stable. They stop changing. Now, with that in mind, from our perspective, in the big macroscopic perspective, from what we can see, we can't see individual atoms, we only see the average results of them. This makes it seem like the reaction has stopped. Imagine, for example, a lineup at a busy grocery store where the number of people that are joining the line is the same as the number of people the rate at which people join the line is the same as the rate at which people get checked out. So for everybody that gets checked out, another person joins the line. If you only took a picture of that line over time and all the people looked identical, you wouldn't be able to tell that anything was happening. It would look like nobody was getting checked out. Imagine you have 3 people in line. They're all identical, and then as this person leaves, everybody else steps forward and another person joins, and from your perspective, before and after the change, so this would be like before and this would be like after, the line stays the same. There's still 3 people in the line. You can't tell that somebody left and somebody else joined in because you can only see the overall big picture. That's what an equilibrium is. The forward reaction is still happening. The backwards reaction is still happening. They're just happening at the exact same speed so that every time an AB is formed, another AB splits, and as a result, you can't see any more ABs being created or being destroyed. So an equilibrium happens when the forward reaction and the reverse reaction balance each other out completely. Let's say that we had 100 A's and 100 B's and 1,000 ABs. And then let's say that these guys 10 of them came together to form 10 new ABs. And at equilibrium, we lost 10 ABs and produced 10 individual A's and 10 individual B's. Because the amount of decrease is the same as the amount of increase, the overall system appears to have stopped. It hasn't, it's just that the number going this way, the forward reaction, and the number going this way, the backward reaction, have become equal. So we can focus on this from the reactants point of view and say, since they get destroyed and created at the same rate, the overall population of them doesn't change. Or we can say it from the products, they get created or destroyed. In the end, the overall amount of them doesn't change. So if the concentration remains constant, how can we tell? Are we sure that the reactions are still happening, or is it possible that the reaction has actually stopped? Somebody did an interesting experiment with this. They took a crystal, a salt, and they saturated it in solution. So they put so much in that no more would dissolve. Now you might say that it had stopped dissolving, or if you're thinking about this as an equilibrium, what you might realize is that the number of ions that are joining the crystal is the same as the number of ions that are leaving the crystal, and as a result, since the forward and backward reaction are happening at the same rate, we can no longer tell that the reaction is happening. It appears as though it stopped dissolving, but the truth is that it's dissolving and crystallizing at the exact same rate. So it appears stable, and we say it is in equilibrium. Now what they did in this experiment is they took some radioactive isotopes, and for the sake of describing this, I'm going to make my radioactive isotopes red. So these ones are the radioactive ones. And after a period of time, they put them, so this is a chunk of salt sitting at the bottom, and there's a bunch of salt dissolved in the water, and then they took more ions of the salt and they stuck them in the liquid. Now if the reaction had stopped, those radioactive isotopes should stay in the solution and they should not become part of the crystal. But that's not what they discovered. What they discovered is that after time, some of these radioactive isotopes took the place of different materials in the crystal. And so what you ended up with was a crystal that had some dissolved radioactive elements or particles in it. See, this guy and this guy must have replaced this guy and this guy, and now this salt is radioactive. So by seeing that, they know that this crystal isn't just sitting here, even though it doesn't appear to be dissolving at all, but what must be happening is that the ions that are leaving the crystal are leaving at the same rate that new ions are joining the crystal, and as a result, the overall size of the crystal has become constant. So that's what an equilibrium is. We're going to talk about in some upcoming videos what it looks like when one of the reactions is a little faster, some common situations where these equilibriums get created, and then we'll get into some of the mathematics of it.